Well, thank you all for being here. My name is Kathy Ludwig. I'm the superintendent of the Wilsonville School District. And I just have to say, this evening and this event has always been, for a long time, one of my most favorite events to attend, to watch students mature into this type of inquiry and work. And it's incredibly inspiring and impressive to see the sophistication of those science projects that we just saw this evening. So welcome to what is our 16th annual CREST-Jane Goodall Science Symposium. We are in for a really incredible evening because we have a fantastic keynote speaker tonight. Chris Goldfinger, who's with us this evening, is a marine geologist and geophysicist with a focus on great earthquakes around the world and the structural geology of the Cascadia margin. Though he has been first author or co-author on over 70 peer-reviewed publications and has worked in collaboration with scientists at some of the leading universities and research institutions in the world, he perhaps most caught the attention of the general public as a primary source in a New Yorker article by Catherine Schultz titled, "The Really Big One." How many of you heard about that? Yeah, there we go. We were just chuckling about that a little bit ago. The article was about the robust science behind predicted impacts of the next big coastal Northwest earthquake. He has advocated tirelessly for relocation of planned building projects on the Oregon coast over mitigation through engineering design alone. Dr. Goldfinger's research takes place on land in his active tectonics laboratory at OSU and also at sea. He has experience with deep submersibles, side-scan sonar, seismic reflection, and other marine geophysical tools on over 25 oceanographic cruises over the last 10 years. He is currently working on great subduction earthquakes along the Oregon and Washington coasts, beginning work on the Sumatra margin, and working alongside the northern San Andreas Fault off San Francisco, using the evidence for earthquakes found in deep sea sediments. Dr. Goldfinger is an associate professor of marine geology and received his PhD from Oregon State University in 1994. His talk tonight is entitled, "The Coming Great Cascadia Earthquake, How Did It Come to This?" Please join me in a warm welcome, Dr. Chris Goldfinger.
Take me just a sec to get rigged up. But thank you for the invitation and for the kind words of introduction. And just bear with me for a second. So I took a little tour of the fair, and I have to say, I could send my graduate students down here to learn some things from your high school students. That was really, really impressive. When I was in high school, I was on the way to dinner saying we were mostly interested in exploding things and making hydrogen gas out of, we made it out of Drano and tinfoil. So it was, anyway, much less sophisticated than what I'm seeing here today. It was really a pleasure to see all that. So now I'm here to dampen the mood as much as I can with some doom and gloom about Cascadia earthquakes. So it sounded like a lot of you had read the New Yorker article and seen something about it. And anyway, there was no new information in that article, and most of the information that was there had been seen in, I think, in 2 different NOVA productions, National Geographic, a number of places. And all of us thought, well, our work is done here. The public all knows about this. And there, now it's on. And so that turned out to be wrong, as it turns out. And when it first came out, a group of graduate students and I were in a meeting in Zurich, Switzerland, and all of a sudden my inbox just filled up like crazy. And I said, I wonder what's going on here. And then it turned out this article had come out. And so that's when we learned that almost nobody knew about Cascadia, and we thought everybody did. So I'm going to go back in time to the beginning of the story and tell you how we know what we know about Cascadia and how did it come to this. So the funny thing about this, you're laughing, but the funny thing about this is geology, Sheldon is actually right. Geology is about 100, maybe 200 years behind all the other sciences. And I get to say that because I'm a geologist, so it's cool. But we're the guys who like to fill up the back of the truck with beer and head off to the mountains and bang on rocks with hammers and things. And so, when we had general relativity being developed in, the early part of the 19th century, geology was absolutely nowhere. We had no clue about how anything worked in geology. Not that there weren't hypotheses about it, but they were all wrong, basically. And so it was really only not until the early 1960s that we started to get a clue. And 1960s is pretty late in the game compared to the other sciences. And so Sheldon is really kind of right when he poo-poos the geologists. So here's the way I like to think of it. So when the Apollo astronauts were on the moon, I was just a kid. I was in junior high school, I think. And my dad, it was really cool. My dad was involved in the Apollo program, built some of the hardware for it. And so we were watching this all on our black and white TV. But at the time, plate tectonics, the ruling theory of all things geologic, was only like 6 years old in 1969. In fact, 6 years is generous. Maybe 4 or 5 would be closer. So here we are doing arguably the most advanced thing humans had ever done. And we had just figured out where mountains came from. And theories before that were sort of like the stork brought it. They were just not even there. And so here's I think this is on Apollo 14, an astronaut setting up a seismometer on the moon to record the moonquake made by the lunar module after they were done with it hitting the moon. And so we had from the late 1960s to now, we had a long way to go to learn all about how the Earth works, and we're clearly not done yet. And so we've had to pack a lot into a short time, and we've learned a lot, but we've also made a lot of big mistakes. And so Cascadia, here's Cascadia, and here we are more or less here, and coastline, continental shelf is here, and then this sharp line here between the deep blue and the lighter blue is the plate boundary between North America. Everything here in green and yellow is North America, and the Juan de Fuca and Gorda plates, which are these oceanic plates here. These lines out here are mid-ocean spreading ridges where new crust is being formed, and it's subducting, basically diving underneath North America at about 35 millimeters a year, which is about how fast your fingernails grow. Seems pretty unimpressive. It's not a high-speed collision by any means. But so when plate tectonics was born, the Juan de Fuca plate was one of the places where they actually used the structure of this in ways I don't have time to talk too much about, to develop the theory of plate tectonics and seafloor spreading, as it was called. And so they demonstrated that, in fact, new crust was being formed here by using the magnetic properties of the basalt rocks on both sides. And so there was a famous paper called Vine and Matthews in 1961 that helped demonstrate seafloor spreading, and it came from right here. And it could be applied around the world, and it seemed to work everywhere. And suddenly, the rows of volcanoes like the Cascade Arc, and the earthquakes that happen in these zones, and the structure of the plate boundaries themselves suddenly made sense all around the world. Everywhere except, guess where? Here. So there was one critical thing missing. Does anybody know what it was? Shout it out. No earthquakes. So Cascadia is the quietest subduction zone in the world by an order of magnitude. And on a regular basis, daily, weekly, monthly, decadally, whatever time span you want to choose that we have records for, it's just dead silent. And so other subduction zones, regardless of whether they make giant earthquakes or not, none of them are anywhere near this quiet. And so at the time, people didn't pay too much attention to that. It wasn't a big deal. But over time, it started to get to be more and more of a sore thumb. Like, why is this subduction zone that helped demonstrate plate tectonics so quiet? And so there were two basic ideas. One was that the tremendous amount of sediment from the Columbia River that had basically filled up the Cascadia Basin, and there normally would be a trench here, a feature called a trench. It had filled that up, and so the idea was that this very wet, unconsolidated sand and mud lubricated the subduction zone so well that it was just slip-sliding away happily, not locking up and not making a squeak. And so, but there are other subduction zones that have sediment. So what's with this one? So that idea didn't exactly catch fire. And the other one was that maybe the configuration of the plate boundary was sort of frozen. It just locked, and not moving anymore. And at the time, there wasn't the resolution. We didn't have GPS, and we couldn't see it was moving on a daily basis. All we had was 500,000 year to 1,000,000 year resolution from the magnetics of the basalts, and they couldn't tell you if a subduction zone had stopped yesterday. And so nobody really published that idea either. But it was out there just as a question mark, and nobody had a better idea. Let's see if this works. Maybe it's not going to work. Dang it. Well, it didn't work perfectly, but anyway, if you recognize that music, I know how old you are. So anyway, as the song Alice's Restaurant goes, there was a third possibility that nobody had counted upon, and that was that the Cascadia plate boundary was completely locked so solidly that it wasn't letting out even a squeak. And that idea really didn't come up until about 1985, when John Adams was really the first person to discover some direct evidence of Cascadia earthquakes. A little before that, a few others had been talking about the possibility, maybe comparing Cascadia to Alaska and Chile that had big earthquakes in the 1960s, the early 60s. But Adams was really the first one to come along and say, hey, I think I have some evidence that this subduction zone is active. And then a few years later, Brian Atwater came along, a USGS geologist, and found some more evidence onshore. And what he found looks like this. So this is in Willapa Bay, and this is the modern marsh surface up here. This is some bay mud, which normally is found a meter or two deeper in the geo-ecosystem. And then a sheet of sand, and then an old peat deposit that it's been, an old marsh deposit that's been degraded and is now peat. And not only that, these dips in it here turned out to be Native American fire pits. So at one time, there was a marsh surface with some fire pits on it, and then some sand covered that, and then some mud covered that, and sometime later, there was another marsh growing on top. The funny thing is, these plants are the same as those plants, and they're really super sensitive to the level of the tide. So somehow, either the sea level changed by that much, or the land level changed by that much. Got two basic options. And so what Brian did was he looked at the top surface of this, and he found that the little marsh plants were not just buried by sand, they were actually entombed by the sand in growth position. So this sand didn't just happen over time, it happened really quickly. And so this old surface was buried by a sand sheet very rapidly, and apparently the land level was lower relative to the sea because intertidal or subtidal bay mud covered that. And then here we are back at a marsh again. So apparently the land had gone down really quickly, and then over time, it had come back up about the same amount. And so Brian's outrageous theory of the time was that this was due to great earthquakes, and this was the entire North American plate flexing downward and then back up. And nobody believed this the first time out. And Brian, he took us, a bunch of us, I was a graduate student at the time, and he took a bunch of us out on field trips and explained this idea. And we just thought, no, that's crazy. There has to be another way to explain this. And we'd all go to lunch and grumble about this crazy idea. And Brian would say, well, see if you can come up with a better one. And nobody did. Oops. And so, so the paradigm change from Cascadia being silent to Cascadia generating big earthquakes started really in 1985, and it didn't take very long. By 1993, Kenji Satake in Japan had found some records of a tsunami that arrived in Japan in the year 1700. And Brian had been carefully radiocarbon dating these deposits and had gotten within about a decade either side of 1700. And a colleague, David Yamaguchi, had also dated tree rings from cedar trees and gotten similar numbers, plus or minus, a decade or so. And then Satake found this tsunami evidence in written records from Japan, where the wave had swept in and had destroyed some rice and warehouses and sunk a couple of boats and things like that. And this tsunami came without an earthquake. And tsunami is a Japanese word, of course, and they're strongly associated with earthquakes. So it was notable that this particular tsunami arrived without an earthquake. And when Satake found the records, then he started modeling this tsunami arrival to see where it could have come from. And he tried Kamchatka, he tried Alaska, he tried Peru, Chile, other places around the Pacific Basin. And really the best fitting model to the coastal records here, which were very carefully kept, essentially for insurance purposes, so that the warehouse owners could get paid back by the shogun for their losses. And probably in those days, the penalties were severe, so they probably didn't exaggerate their claims very much. And so the best source for this wave was really Cascadia. And so that's how we know today that the last Cascadia earthquake was January 26, 1700, about 9 o'clock at night. Kind of a tidy little story for geology. We're not used to that kind of precision. So anyway, that was sort of a triumph of sleuthing, really, that we could actually figure out the date and time and time of day of an earthquake 300 years ago. And so here's sort of the sequence of events. In a subduction zone, the continental plate, the one we live on, is the weaker of the two plates. The oceanic plate made of basalt is much stronger, and so it flexes upward as the plates are locked here, just flexing upward like this. And then, and that goes on for several hundred years while it's accumulating elastic strain energy. And then during the earthquake, whoops, wrong button. During the earthquake, that releases, and so the part that was going up goes down. You have subsidence along the coast, and the outer part goes up, and that long wavelength change in the upper plate over a couple of minutes is what generates the tsunami that goes off in both directions. And on land, what you see is this. You have a forest growing down to the shoreline in some of these bays. And then suddenly, over a span of 2 minutes, it drops a meter into the bay. 20 minutes later or so, the tsunami comes in, lays down the sand sheet. And then this is underwater for some period of at least decades, maybe hundreds of years. And so that's where the bay mud comes from. And then the saltwater intrusion kills the trees. And as you drive along the Cascadia coast on almost any bay, you'll see these dead snagged trees along the shore. And it turns out that some of these trees, the western red cedars that are well preserved, are actually not recent snags, but they're 300 years old, and they've been standing there since the last earthquake. So next time you're driving around the coast, take a look at those in a slightly different light. So lots of things happen during earthquakes. You have the whole coastline flexes and goes down. You have landslides onshore, forming lakes and things like that. Offshore, you also have submarine landslides. The same processes take place underwater. So this is a cutaway of Cascadia. Here's the Juan de Fuca plate. Here it is subducting obliquely 35-ish millimeters a year. And this big pile of blue stuff out here, this is essentially all the Columbia River sediment that's been accumulating for the last 40 million years or so.
all essentially snow shoveled off the Juan de Fuca plate by North America. And so this is called the accretionary wedge. And it's just this pile of, just like what you'd have in the front of a snow shovel. And so when you have a submarine earthquake, it generates submarine landslides which sort of transform into turbidity currents, which are just slurries of sediment running down the hill that look kind of like this. You can recreate this in your fish tank if you have one. The fish might not like it much, but... and so this kind of chaotic, messy process deposits sand and gravel and silt in the deep sea. And when you go out and take a core on a ship of these sediments, it looks kind of like this. And so if we're to just do a cheap visualization of what that might look like, this is Astoria Submarine Canyon, my cheap attempt at animation. You have all these submarine landslides that coalesce and run on down the slope like that. And then if you, whoops, let's go to the next slide. So if you turn all of Cascadia on its side just to make it fit the screen a little bit better, it would look something like this. So all of the submarine canyons feeding turbidity currents simultaneously out into deep water. And so you go out on a ship with a gigantic lawn dart. This is about a 30-foot long lawn dart with 4,000 pounds of lead at one end and a 300-foot ship at the other end and a wire. And you collect samples in 4-inch sprinkler pipe like this. And these are the turbidites, they're called, the sand layers in there. And so they're relatively easy to capture, but the job is trying to figure out what they mean. Can you do something useful with them? And so I mentioned that this Canadian geologist named John Adams wrote an abstract. You guys all know what abstracts are now. And in 1985 for the American Geophysical Union meeting, and what he said was that there were cores out there in the deep sea. This is all the deep blue part, and up into here is in about 3,000 meters of water. So it's fairly deep water, shallow for a subduction zone, but pretty deep. And these cores in gray and white had been taken in the 1960s by OSU students, and these cores still exist in the OSU Core Lab. And so John took these cores. They actually didn't even visit OSU. He just got the core logs faxed to him from some of the faculty at OSU. And he started investigating these cores and wondering if you could learn something about earthquakes from them. And one of the very first things he noticed was that in these white cores, and many others, this is just simplified here a little bit, there was an ash layer from Mount Mazama, that's Crater Lake. It went off 7,650 years ago, plus or minus about 100 or so. And so it deposited ash in all the river systems in the Northwest, and that ash came out the rivers and wound up on the shelf, and eventually wound up in the deep sea in these cores. And what John noticed was that in those turbidite layers, that stratigraphy, the ash was 13 turbidites down in here off the Rogue River, here in Cascadia Channel, here in Willapa Channel, and here in Juan de Fuca Channel, and also here in Astoria Channel, right off the Columbia River. And so the first thing he asked was, why would you have the same number in all those different places? I mean, these submarine landslides could be caused by storms, they could be caused by 3 different types of earthquakes, crustal earthquakes, slab earthquakes, and plate boundary ones. Maybe even exotic things like the destabilization of gas hydrates, basically frozen methane in the sediments. And so if you have a laundry list of 6 or 7 things, why would you, occurring at random times, more or less, why would you have the same number of turbidites above the ash in all these places? And his first thought was, well, earthquakes could explain that pretty easily. Because earthquakes are really the only process that could encompass this whole area all at once. And so he went a little bit further, and he thought, well, okay, so if it's earthquakes, then all of these would have to have been deposited synchronously. And synchronously means minutes. It's like, but how do you tell geologically whether something happened within minutes of something else? Well, you can't. There is no way to do that. So he was stymied for I'm not sure how long. I'll imagine hours, if not days. But maybe it was minutes. John's a pretty smart guy. So his question was, radiocarbon only gets us to within a few decades. So what do we do to figure out whether these happen at the same time or not? And so what John did is what we all do when faced with a difficult problem: we cheat. And so John realized that we don't actually have to know when these things happen in absolute time. All we have to do is figure out if they happen at the same time. And so he decoupled himself from the mechanism of radiocarbon dating and all of that. And so what he looked at was, there's a confluence here between two major channel systems here, the Willapa system and the Wanda-Fuca system here, and they come together at a confluence. And both arms of the confluence, this one and this one, both have 13 post-Mazama turbidites. You go below the confluence, the number stays the same. It stays at 13. So you only have two possibilities. One is that either you got to the confluence and you really had 26, or some number between 13 and 26, and you lost some going downstream. Or the other possibility is all 13 in a row got to the confluence at the same time basically within a few hours, and went on happily downstream to deposit the same number of 13. And so it turns out that the second hypothesis was correct. And so John, sitting at his desk, never went to sea, never actually has even seen these cores, figured out that 13 times in a row we had great earthquakes that ruptured all the way from the Rogue River to Vancouver Island in 7,000 years. Sitting at his desk. Now, in geology, that's elegant. So, not being nearly as smart as John Adams, we went to sea and did it the hard way. And we went out to test this hypothesis. And the reason we did was that basically several of us, in fact most of us who work in Cascadia, really didn't believe it at first. And so I worked with a colleague who'd worked on the Astoria submarine fan right off the Columbia River, and he came up to me at a meeting and he said, Chris, there aren't 13 turbidites after the Mazama ash, there's only 3. I know because I did my PhD thesis there. I've got all the cores. I collected all the cores that Adams used. So here's a guy telling me that the guy is wrong. And so we decided to write an NSF proposal to prove John Adams wrong. So we went out to sea and collected a whole bunch of nice new cores with modern equipment, collect all the geophysics from the cores, and did it the hard way, not the elegant way. And we used CT scans of the sediments, all sorts of fancy things, and just dug into these sediments in great detail. And so what we used is we used the physical properties of the sediments. And so here's some core samples. And these little wiggles you see off to the side. One of them, let's see, on the right side, this is grain size. This is magnetic susceptibility. This is density. And this is P-wave velocity. So these are basic physical properties of cores. And these techniques are basically data that's collected from the cores in the same way the oil industry uses to track oil-bearing sands around the Gulf of Mexico or the North Sea. So we just borrowed this technique for correlation. And it turns out that these wiggles tie to the sand in the cores. So every time you get a peak grain size or a peak density or peak magnetics, it represents sand. So these are just what are called proxies for grain size. And it tells us about the structure of the sediment, and that's going to be important in a second. So if you zoom out from that one example, these are some examples of sections of cores with these turbidites, and each one of these kicks here represents one of these turbidites. So higher density, higher grain size, higher magnetic properties, and so forth. So these are all turbidites. And what we found pretty quickly was you could correlate these cores pretty straightforwardly amongst cores that were close together and also cores that were far apart and cores that were not in even the same channel systems. So, whoops. So Rogue Channel and Hydrate Ridge are two sites that are 250 kilometers apart and have no communication between them whatsoever, and yet you can correlate these things quite well. And the numbers you can't read here are the radiocarbon ages, and I didn't want you to fixate on those, so I just put those in the background. But essentially, the radiocarbon ages have full overlap for these two. So it appeared that not only could you find the turbidites, count them easily, find the Mazama ash, here it is at the red line down here, date them and get more or less the same age, plus or minus 100 years, but you could correlate them directly and use their shape to help do that. So we were kind of testing Adam's hypothesis, which we started out to disprove. And what happened was we started to put this together while we were at sea on the script ship Melville. And they have a tradition on these ships that you give a show and tell to the ship's crew, just as a thank you and to show them what you're up to. And so in the middle of this cruise, we pulled out all the cores out of the freezer, laid them all out there, and my colleague Hans Nelson and I looked at this and we went, you know, every one of these cores has 13 turbidites above the Mazama ash. So what are we going to tell everybody in our show and tell? And so right then and there, our paradigm changed. We realized that John Adams was right. So that's what we told the crew. And so the ship's engineer came up to me, and it was great. He comes up to me and he goes, you know, I've been working on this ship for 25 years, and I hear the scientists talk about all the stuff they're doing, and I have no idea what they're talking about. He goes, but I can count to 13, and I understand that. And so our paradigm shift was right then and there, and that taught me a valuable lesson about, you know, don't hang on too tightly to your pet ideas because they may just be gone, you know, that quickly. So then I became a paleoseismologist and started, because Hans Nelson and I started out on this cruise thinking we would dispose of this crazy hypothesis and beyond to bigger and better things. And instead, we both became paleoseismologists, study of past earthquakes. And so this is our preferred field vehicle. This is the UW ship Thomas Thompson. It's 270 feet long. Usually when we go to sea, we have a total of about 55 or 60 people, 20 or 25 crew, and 30-ish scientists or so. And we've got a big crane and an A-frame, and we can take these core samples in 6,000 meters or more of water. So this is the kind of tool that you normally need to do offshore deep water paleoseismology. But it turns out that you can also go to lakes around this area and find turbidites in lakes as well. And so here are some of my students and technician. You might recognize the green background as a Grumman canoe, and here's a sheet of plywood over the top. So we have two Grumman canoes tied together in a nice little catamaran with a hole in the middle, and collecting these hand-pushed cores. And guess what we found? We found turbidites that were just like the offshore ones. Only instead of $50,000 a day, this was more like $100 a day to do this. So we're now working on a corridor through Seattle and through Portland. We're actually working at Bull Run Lake with some support from the Portland Water Bureau. And the reason we're doing this is that all of our paleoseismic evidence for these earthquakes is offshore or along the coast. But kind of oddly for Cascadia, our big cities, Portland, Seattle, Vancouver, Victoria, they're all 150 kilometers inland. So the data is over here and the hazard is over here, the risk is over here. And so we're trying to bring the paleoseismology closer to the cities so we can give the engineers the numbers they want. So the engineers are sitting there. As we speak, operators are standing by with a blinking cursor going, just give us the number. How big is the earthquake? And we'll design for it. And the answer to that is hard to come by. It's easy to find an earthquake and find evidence for an earthquake, but how big was it? That's tougher. And so that's why we're working on lakes. And so it turns out that you can correlate these lakes together just as we did offshore. Here's a lake near Seattle and a lake near Hood Canal. And without going into the gory details, you can correlate the lakes together and correlate them to the offshore. And that helps tie the whole story together. And here's a really nice, pretty picture of Bull Run Lake. This is a great place to work because it's sort of a de facto wildlife refuge. Nobody's been allowed in there other than the people who worked on the water system since the 1930s. So all the wildlife they just walk up to us and the deer and everything and just, oh, what are you doing there? And so we put a barge in the lake and took cores there and had a couple of nice, enjoyable summer days on Bull Run Lake. So the bottom line for all of this is that about a dozen scientists and a host of graduate students, probably roughly 100 people over 30 years, have been putting together the story of earthquakes at lots and lots of different sites. Virtually every coastal bay, starting with Brian Atwater's work in Willapa Bay, and then almost every other coastal bay, from Vancouver Island down to Humboldt Bay. And then we've got the offshore turbidite evidence. And now we've got lakes as well. So we've got a lot of lines of evidence that are telling us the same story in slightly different ways. And so Cascadia has gone from being just this enigmatic question mark where we knew nothing about it to suddenly now it's the best known fault in the world, even though we haven't had a big earthquake in recorded history. So what if all of this that I'm telling you was true? And we could actually map out the time and space of all these earthquakes using all this data. Well, I think you can, and so this is it. This is Cascadia the movie. So it's not as good as the San Andreas movie. The graphics are not up to Hollywood standards. And sorry, The Rock isn't in it either. But anyway, this is the real deal of Cascadia. So we're going to start at 10,000 years ago and play at about 200 years per frame per second, and what you'll see is some red blobs on here, and you'll see some colored dots, and those represent the data points where the earthquake information came from. So it starts out pretty sparse at 10,000 years ago and gets filled in as we go. And you'll see some red blobs appear like that, and the bigger and redder they are, that's an indicator of earthquake relative size based on the data. And so what you'll see is a series of big ones, and you'll see some occasional smaller ones. There's a really big one. So there, Crater Lake goes off. There's the ash-bearing T13. Very small one down south. Another faint one, but full length. Here's the biggest one of them all, T11. After T11 happened, Washington had a 1,200-year gap, and the southern margin had 5 events on a 250-year spacing, more or less. Now we're down to about 4,100 years ago. 3,500 years ago, T8. And now the land record kicks in, and you'll start seeing more colored dots along the land. And down here, you'll see actually the San Andreas going off, where we have also a 10,000-year record of the San Andreas. And you might notice that they're going off, most of them go off at about the same time as Cascadia, setting up a new grade B movie scenario where one of these faults may trigger the other, and they may actually go off more or less at the same time, which we can't exclude from the data. So maybe The Rock will have a whole series of movies. We'll see. And so here we are at AD 1700, the fabled Cascadia orphan tsunami. And it turns out that the recorded history of the Cascadia earthquake wasn't only in Japan. Once the geologists had figured this out, the Native Americans just said, oh, why didn't you just ask us? We knew about that. And they did. So they had a legend called the Battle of Thunderbird and Whale. And during this battle of two great Native American gods, there was a lot of crashing and banging of the earth and a lot of washing away of villages. And they realized that this sounded an awful lot like an earthquake and tsunami. And so as near as anyone can tell, the Battle of Thunderbird Whale was the Native American record of the 1700 earthquake. And so it came with a an asterisk which said, to the people who told this tale, oh, by the way, don't build your villages too close to the ocean. And so this is a summary of what that movie looks like. So there are 46 earthquakes that are geologically recordable, either offshore or onshore or both, in the last 10,000 years. There are about 19 of them that run the full length of the margin, or more or less the full length. 2 or 3 more that stop a little bit short in Washington. About 8 more that stop at about the Columbia River. 2 that stop at about Newport. About 8 or 9 more that stop at about Cape Blanco, and a few more that are a little bit further south, and 1 single one that just affects, apparently, Washington only. So as we learn more and more about Cascadia, we're learning that the earthquakes are pretty diverse. They're not all the same. They're not all magnitude 9s. The magnitude range probably goes from mid to upper 7s for something like this, up to 9 or maybe even 9.1 for the maximum size for this. And the rest of these are arrayed somewhere in between. And magnitudes are tough to come by without any real instrumentation. But there we have it, and there are the core sites in black offshore. So Cascadia, anyway, I mentioned, has come to be one of the best-known faults in the world now, even though we're still waiting for our first instrumental earthquake. And so this gruesome plot, well, not gruesome for this talented crowd, but so this is a log plot showing, it says unreliability. That means unreliability of the Cascadia fault as a part that's going to fail, from 0 to 99, and time going from 0 more or less out into the future. And so if you want to know what probabilities are, and as humans we'd kind of like to know if we should worry about this or not, here's what you do. So you map out, and this is the only fault in the world that you can do this for. So let's look 50 years into the future and say, what's the probability in the next slice of 50 years? And that's roughly 360 years from the last earthquake when I made this plot. And so these dots are for the northern part of the margin, basically Washington. These dots are the recurrence times between pairs of earthquakes. So there are 18 of them or so. And you can see that off here to the right, which is the future, most of the dots are off in the future. So this means that the probability is fairly low, and we haven't even reached the median time for these earthquakes, which is 430 years for Washington. It's been 316 since the last one, so we haven't even got to the average yet. And so that means the probabilities for Washington are modest at best. In the next 50 years is about 14%. So then let's flip-flop down to Southern Oregon and make the same plot. So now they have almost twice as many earthquakes, actually a little more than twice as many. And we go out 360 years from the last earthquake, 50-ish years from now. And we see that there are only 6 dots out here in the future. This means that we've gone past 75% of the intervals since the last in the Holocene time in 10,000 years. And there's only 6 that are longer than the present interval, 316 years. So, as you can imagine, that changes the probabilities. So in the next 50 years, it's close to 40% probability that the southern half of the margin will have some geologically recordable earthquake. And the threshold is about magnitude 8, roughly. So this is 7.9 was the earthquake that destroyed San Francisco in 1906. So when I use the word smaller, they're not small. They're still big earthquakes. And Portland and the area, say, between Newport and Portland is kind of in between these 2 plots, and they fall in at around 20 to 22% probability in the next 50 years. So if you're wondering whether to worry about this versus asteroids hitting the Earth and various other things that you could worry about, these numbers are huge, actually, for probabilities. The Tohoku earthquake in Japan, in 2011, that fault failed when they were sitting at about 20%, just about where we are now. So you don't have to wait till 100%. It can fail any time during that time. So these are actually pretty big numbers. And this is what sort of spawned the New Yorker article that went viral and made everybody freak out. But there's always problems with trying to estimate and calculate these things. And when you calculate probabilities like that, the assumption is that the earthquakes are spread out evenly in time. Otherwise, you can't really calculate anything. But it turns out they're not spread out evenly in time. So here's 10,000 years back here. Here's 0. The red you are here dot is right there. And so, but these earthquakes are clustered. So there's 5 of them together. There's a 1,000-year gap right there. There's 5 more together and another 1,000-year gap. And then it gets a little less clear what's going on back here. And so they're just 2 different versions of that clustering behavior. And so we're wondering, now we're sitting here, well, does this cluster have 1 more in it or not? I wish I knew, but we don't. And we don't even know whether this behavior is random or whether it's physically driven by some tectonic process. You could, if you just flip coins, essentially do a Monte Carlo simulation of this, essentially flipping coins, you can reproduce this about 20% of the time. About 80% of the time suggests, though, that, that this is not random, that it's probably driven by something. But so when you try to calculate earthquake probabilities and the hazards and risks, something like this just completely monkey wrenches it because we have no way to look into the future and see what's next. It's like predicting the stock market or something like that, even less predictable than that. So anyway, we can at least hope that our earthquake is going to be like this. But sadly, it's probably not the case. It's probably going to be more like this. And so, I hate to put up these doom and gloom pictures, but this is actually what success looks like. So Japan is the best prepared country in the world for earthquakes and tsunamis. And so in 2011, they had a magnitude 9 earthquake. In 2004, Sumatra had a similar, it was a magnitude 9.15, a little bit bigger. But around the Indian Ocean, we lost nearly 250,000 people because there was no preparation and no level of education about great earthquakes and tsunamis. Japan had a very similar event, and they lost 20,000, which is still a gigantic number, but it's 10 times better, an order of magnitude better than Sumatra. So this is the difference between success and failure, I guess, in one of these catastrophic events. And so you might not look at these pictures and go, oh yeah, that looks like a win to me. But actually it was. And the only thing they did wrong was that they'd actually gotten the geology wrong. So they were very well prepared, but for the wrong earthquake. They prepared for an 8.4, and it was national policy that was the maximum size earthquake for Northeast Japan, and that turned out to be wrong. So the geology just hadn't caught up with the preparation, which is kind of a funny thing. In Cascadia, we're just the opposite. So we think we have the geology pretty well in order, but we're roughly 1,000 years behind in preparation. And so here are just some of the vulnerabilities. So we have a lot of unreinforced masonry buildings, bricks, basically. And the way engineers describe this is that they're built for gravity loads, meaning they won't fall over by themselves, and built for wind loads, so they won't blow over in a breeze. And that's it. That's pretty much. So there's no steel in these buildings, and they really have no ability to perform in earthquakes at all. So this nearly destroyed building was wrecked in one of the little 4 to 5 fracking earthquakes in the Midwest. So this is really all it takes to destroy a building like that. And so in Vancouver, Victoria, Portland, and Seattle, about 70% of our cities, including the OSU campus, I might add, are built like this. So the places we go to school and the places we work in typically are in trouble, So we have a lot of bridges in Oregon. Some of them look so spindly they really don't look like they'd stand up in a strong breeze, to me. I'm not an engineer, and also drawbridges with their big counterweights also don't do well in earthquakes. So we have a problem with the Portland bridges. We have a problem with all of the bridges across the Columbia and across the coastal bays. And then we're in a high school. So in Oregon, we have about 1,000 unreinforced masonry schools. And schools are kind of a, I think kind of a special place. So we definitely have a problem with these. And in the Pacific Northwest, we have about 3,000 of them total. So when I say we're 1,000 years behind Japan, I'm not exaggerating. So they're so well prepared because they've been hammered again and again and again by earthquakes. And they finally, as a national policy, decided to say, enough. We're just going to raise the standards of everything so that the whole society is resilient enough that an earthquake there is more or less just an exciting bad day. And not counting the tsunami is a much harder thing to deal with. But when you walk around Japan, and I was there for the 2011 earthquake, if you walk around the parts of Japan that weren't inundated by the tsunami, it was hard to notice that anything had happened at all. I was stuck there because the airports were closed and so on. And I went to a farmer's market, and they were just selling pottery, and everything was just going on as normal. And that's because they've had 1,000 years of going through this cycle again and again and learning how to do it better, and then better and better. So we have somebody to emulate, And so this is I'm going to show you a slide or two from Minami Sanriku in Japan. And here's what it looked like right after the tsunami. And you notice the water is still there, and that's not because the tsunami hasn't receded. It's because the land level has dropped semi-permanently about a meter or so. And so at high tide, the whole thing is more or less underwater. And so what they've decided to do is, this is that section of town sort of rotated a little bit. So what they've decided to do is this. So this is the present ground level where the cones are. They're going to raise the ground level of Minami Sanriku up to here, 4 meters higher than it was before, with fill. And then they're going to put the town, which was completely wiped out, on top. And so that's the sort of value the Japanese place on sort of beefing up the infrastructure for earthquakes. And they're quite serious about it. And so when we were there a couple of years ago, we got a tour of the Minami Sanriku Hospital. And here's another example. So this hospital is base isolated, meaning the whole hospital is built on rubber donuts. So when the earth moves, the building doesn't. And so this engineer is showing us some evidence for that. And they had just finished this hospital when the earthquake happened. And they didn't break so much as a light bulb. The phone started ringing, and the ambulances started coming in, and that was it. So there was no messing around with hospitals. And they built this brand new hospital just after they'd finished another hospital they discovered was in the tsunami zone. And they said, well, you know what? We're not going to just roll the dice. We're just going to build another one. And so they did. So you can see that they put life safety and the safety of generations into the future in kind of on a different plane than we're used to thinking about. They think not 10 years ahead or 20 or 30. They think hundreds of years ahead now, realizing that it may not be their children or even their children's children that are going to ride through the next earthquake, but it really doesn't matter to them. Somebody will ride through the next earthquake. And so they think that far ahead. And so this is Mayor Sato. He was the mayor of, and still is, the mayor of Minami Sanriku when the 2011 tsunami happened. And this was the public safety building of the town. And you can see the town is gone. It was in the background here. It's just a meadow now. And this is the last building standing anywhere near the water. And there were a number of people in this building who died transmitting warnings about the tsunami on the radio. And that's why all the radio gear on top of the building. And Mayor Sato was in the building, and this was his view of his town during the tsunami. So he survived by hanging onto the cell tower on top. And he saw the entire town just go underwater. And we interviewed him, and Mayor Sato, what he said was that he was a very sober, as you can imagine, individual. And he said that when he was a little boy, they had told them to evacuate the town because the tsunami was coming from the 1960 Chile earthquake when he was a little boy. And so they did. And they were very disappointed to see only a very small wave come into the bay and nothing happened. So fast forward to 2011, and he's the mayor of his town that he grew up in. And the scientists and engineers were telling him, oh, the maximum tsunami we'll ever have will be about 6 meters or so. So that's what you can use to plan for safety and whatnot. And so then here he sees his town go underwater with a 15-meter tsunami instead. So he said, I just really don't listen to scientists much anymore. And so here's a guy who's learned from experience, how to deal with the problem. So when we come back to the Pacific Northwest, now we think we have the geology pretty well done, and the coastal paleoseismologists are essentially getting the same results as we're getting offshore. So that's always comforting in science when you come at something from many different angles and you get the same result. So our problem in the Pacific Northwest is probably not the science. We're not going to get badly surprised by something that nobody has envisioned or found evidence of, as happened in Japan. But unlike Japan, we don't have a top-down view of public safety. We sort of leave this up to individual communities and entities to make important decisions. And so along the coast, we have people now wrestling with this brand new information, essentially. I mean, to me, it's 20 years old, but since the New Yorker article has educated a number of people, it's new information to a lot of people. And so different communities are making, kind of wrestling with this and making different decisions. So in Gold Beach, for example, they built a new hospital that was put back in the tsunami zone and was legal based on sort of a loophole in the legal status of tsunami modeling in Oregon. On the other hand, Seaside High School, after 2 tries, got a bond measure passed, and now they're moving their high school out of the tsunami zone and on the dry side of Highway 101, which is great. And that was the cool thing about that, which you may have heard of, was that the first bond measure failed, and then the kids in the high school started a GoFundMe campaign to raise $200 million to move the high school. And so who knows whether, they probably would have never gotten to 200 million, but they got the ball rolling, and Weyerhaeuser donated some land, and the second bond measure passed, and now they're doing it. So it just goes to show you, how much power you have, even as high school students, to make changes that need to happen. So ironically, I work at OSU, and OSU is going the other direction. They're actually building a school in a tsunami zone on purpose, which has got me scratching my head for sure. I can't figure this out. This is the Hatfield Marine Science Center in Yaquina Bay. There's the Yaquina Bay Bridge. There's a marina and the Rogue Brewery and a big parking lot. And then all of this is OSU and some state and federal agencies that have been building offices and marine research sites on this sandbar since the 1960s. In the 1930s, this sandbar was not even above high tide. And so since that time, they've added a little sand to it and made it just above high tide. And so we had this science complex here. And OSU was granted from a philanthropic donor some money to build a new science center there. And so despite all the opposition from the entire geosciences faculty, they're going to go ahead and build on this land. And so anyway, we have kind of a hodgepodge of decision-making going on, some good decisions, some bad decisions, some in between. And so unfortunately, in the US, there just isn't a pervasive sort of view of, that the Japanese have the longer view of, what should be done. So in the time lifespan of this building of maybe 100 years instead of 50 years, we're looking at a 30 to 40% probability that building will be destroyed. And so from the point of view of a geologist, geologists are like the Japanese. We have the longer view of things. And so we see this as this sandbar will once again be a sandbar someday. And we hope it happens peacefully and without a school building on it when that happens. So that's my story of doom and gloom for the night. And I'm happy to hang around for questions if you have some. So thank you.